confidence intervals for a proportion. Let me remind you that in lecture 18 we talked about confidence intervals. Confidence intervals are always estimating a population parameter based on the information from a sample. And they consist of two parts. The point estimate is your best guess based on the sample of what the value of the population parameter should be, and your margin of error gives you a sense of the range of possible values. Specifically, point estimate plus or minus margin of error gives you the range of plausible values for the parameter, and your confidence level, which is often 95%, tells you how confident you are that that interval of values contains the quantity you're interested in, which is the population parameter, the thing you don't know. Today we're going to learn how to find that point estimate and margin of error when we are estimating the population proportion for a categorical variable. So the starting point will be a categorical variable, and let's start with an example. Suppose we're interested in the proportion of all college students who disbelieve in evolution. And to explore that, we're going to take a simple random sample of 1,012 college students, and we're going to find the sample proportion. So that's the percentage of that sample who disbelieve in evolution, and let's say that we get 24%, or 0.24 for that. As we said last time, the sample proportion, 24%, is the point estimate for P. It is the best guess based on the sample of what P should be. But to get a confidence interval, we need to ask how different values of P affect likely values of P hat in all samples. That is what lecture 15, which was section 7.1, told us. It told us that if the population proportion is P, and you take many simple random samples of size n, then the distribution capital P hat of their sample proportion satisfies three things. Under favorable circumstances, it will be normal, its mean will be P, and its standard error will be this formula, square root of P, 1 minus P over n. Remember, standard error is the standard deviation for a sampling distribution. When I say it's a sampling distribution, remember, I'm saying the probability experiment is pick a sample and compute P hat. That's a thing you can do over and over again, and you'll get many different samples. So your sample space is the set of all possible samples out of your population, which is an immense sample space. Okay, and all of that assumes not only that it's a simple random sample, but also the rule of 15 and the large population rule. I'll remind you of those later on when we turn this into an explicit procedure. So that tells us, under favorable circumstances, that the distribution of P hat is a normal distribution with mean P and standard deviation square root of P 1 minus P over n. That tells us everything about, once we know P and n, that tells us everything about what P hat is likely to be. In particular, we know that in a normal distribution, 95% of the data falls within 1.96 standard deviations of the mean. The data here, remember, is samples. So that tells us that 95% of samples will give you a sample proportion P hat within 1.96 standard errors of the population proportion P. I'm going to re-say that in two slightly different ways, but it's the exact same statement. So if its distance from P is less than 1.96 standard errors, that means it's somewhere between P minus 1.96 standard errors and P plus 1.96 standard errors, or more concretely, more tersely, P hat lies in the interval P plus or minus 1.96 times the square root of P 1 minus P over n. That's not a confidence interval. It's actually what's called a prediction interval. We're 95% sure that P hat, if you take a sample, will lie in that interval, which is defined in terms of P and n. We want to kind of reverse that and find an interval where p is likely to be in terms of p hat in n. And we'll do that by rephrasing this fundamental fact. So there's the fact again. And let me just ask you a very simple question. If I am within 10 feet of you, how close are you to me? Well, of course, you're within 10 feet. That's how distance works. So if p hat is within 1.96 standard errors of p, then p is within 1.96 standard errors of p hat. So for 95% of samples, the population proportion p is within 1.96 standard errors of the sample proportion p hat, and again we can rephrase that in two ways. That means p is in the interval from p hat minus that quantity to p hat plus that quantity, or more tersely, p is in the interval p hat plus or minus 1.96 square root of p 1 minus p over n. So what we've just given is a confidence interval. 95% of the time, that interval will contain the thing we want to estimate, which is the population proportion p. As a confidence interval, it only has one flaw. The flaw is it depends on p. We're trying to estimate p, and our formula that estimates it needs you to know p to compute it. So it's completely circular. And that sounds like a fatal flaw, but we should think of it as just a glitch, and we can fix that glitch if we're willing to approximate a bit. I told you when we discussed this formula, square root of p 1 minus p over n, that one of its properties is that it is insensitive to p. By that I mean modest changes in p produce very small changes in this quantity. Why is that? Because when you multiply p times 1 minus p, if one gets bigger, the other gets smaller, so the product doesn't change much, and the square root dampens the change even more. So, we will introduce very little error if we replace p by something that is not too far from p. The rule of 15, remember n times p and n times 1 minus p are both big enough, essentially guarantee that p hat will rarely be very far from p, which means that p hat is a decent approximation of p. We're going to find out exactly how good, but before any of that, we can say it's okay. So we're going to replace p with p hat in that formula because modest changes in that value create small changes in the result. This doesn't have much of an effect. So we conclude that in pretty much 95% of samples, p is within 1.96. Now the standard error is computed with p hat, root p hat 1 minus p hat over n of p hat, or is in the interval p hat plus or minus 1.96 square root of p hat times 1 minus p hat over n. We still call that the standard error, even when it's computed with p hat. So all that is exactly what a confidence interval needs to be. So we conclude that the 95% confidence interval for the population proportion p is p hat plus or minus 1.96 times the standard error. So as a procedure, if I ask you to estimate, to give a 95% confidence interval for the population proportion p for a categorical variable based on a sample of size n and a sample proportion p hat, so the problem will have to tell you n and p hat in some form, you conclude that the 95% confidence interval for the population proportion p is this formula. I won't read it out again since I'm getting kind of tired of the square root business. And this procedure, as all our procedures will, comes along with 3 assumptions that you have to check in order to believe the validity of this conclusion. They are familiar assumptions: simple random sample, the sample has to be an SRS, large population, the population needs to be at least, the population size needs to be at least 20 times the sample size. And the rule of 15, but now once again, we don't know p, so we can't check the rule of 15 in its original form, but once again, p hat is reasonably close to p, and the rule of 15, with this step in mind, was built with a lot of padding. So if the rule of 15 with p hat in it is satisfied, then whatever p is, it will still be close enough to meeting the rule of 15 that the normal assumption works. So in the confidence interval, our rule of 15 will use p hat instead of p, but otherwise will be the same. We'll see a couple of versions of the rule of 15 that all use the best version of p that you have available. Okay, that's the entire procedure, except it only tells you what to do if you're looking for a 95% confidence interval. So what if you were given a different confidence level, like 90 or 99%? Well, the only place we used 95% in that procedure was using the fact that 95% of data in a normal distribution is within 1.96 standard deviations of the mean. So a different confidence level only changes that number 1.96. What is that number? It's z star. So remember, if c is a percentage, then c percent of your data in a normal distribution is within z star sub c standard deviations of the mean. So in general, if somebody asks you for a c confidence interval, you would write the same formula, but now with z star c in place of 1.96. How do you find z star c? Well, I gave you a formula that involved norm inverse. It's slightly complicated. That will always work, but I'm not going to hold you responsible for that. All I'm going to do is, all I'll ever do for confidence intervals for a proportion is give you one of 3 confidence levels. So you just need to know the z star for those 3. And they are 95%, whose z star is 1.96, 90%, whose z star is 1.645, and 99%, whose z star is 2.576. You will find we do 95% often enough, you'll remember 1.96, and that will be a really good thing to remember. The other 2 you should have written down. Alright, we are at last ready to face our example. Remember, we were looking for a 95% confidence interval for the proportion p of college students who disbelieve in evolution, supposing that a simple random sample of 1,112 college students gave you a p hat of 24%. Okay, so the answer is the 95% confidence interval for the proportion of all college students who disbelieve in evolution is, there's the formula, so we have to plug in to that p hat. P hat is 0.24, because we're told p hat was 24%, plus or minus the z star, comes from the confidence level. Told we want a 95% confidence interval, so z star is 1.96. Again, we plug in p hat and 1 minus p hat, and we divide by n, which is the sample size. That's a straightforward calculation to do. Let me do it with you the first time. There's a lot that's easy to mess up on that. So I'm going to go to Excel, open up a new file, just so we have lots of space, and I'm going to take the square root of p hat is 0.24 times 1 minus p hat. I like to do that in my head, 0.76, but you could also do open parentheses, 1 minus p hat, close parentheses, divided by 1112, close parentheses. That's my standard error. My standard error is 1.2, and my margin of error is 1.96 times that quantity. So 2.51 let's see how that compares, to what I got the last time I did this. We get 0.0251. Or I like to report my confidence intervals as percentages when we're talking about proportions, because I find percentages are easier to get a picture of. This is an acceptable way to leave it. 24% plus or minus 2.51%. Remember, the best way to report confidence intervals is in a sentence that contains all the basic information. So this is your template for such a sentence. The sentence says the 95% confidence interval for the proportion of all college students who disbelieve in evolution is 24% plus or minus 2.51%. This contains the confidence level, 95%. It contains the full parameter, which is the proportion of all college students who disbelieve in evolution. And within that is the actual parameter, the proportion, the population, which is all college students, and the variable, which is whether they disbelieve in evolution. And the sentence always ends with the point estimate plus or minus the margin of error. You should know those names. Let's do another example. Oh no, let's check our assumptions, sorry. That was our conclusion. We have to check our assumptions. There are 3 assumptions. Simple random sample. Is that bad? Yes, it says it's a simple random sample. Large population. What would we need for that to be true? We would need there to be at least 20 times 1,012, or about 22,000 college students. We don't know how many college students there are, but there are almost certainly more than 22,000. So that probably would just cover UConn. And the rule of 15, remember you use p hat, so it's n times p hat, which is 1,012 times 0.24, which is 267. That's certainly more than 15. We also need 1,112 times 1 minus p hat, or 0.76, which is 845. That's more than 15. So all assumptions are met. Finally, let's talk about the interpretation. So typically I will ask you to find a confidence interval, and I will usually, though not always, ask you to check the assumptions. If I don't, you don't have to. And I will occasionally ask you a question about the interpretation. Here is the interpretation of that confidence interval. It is subtle. Remember, each sample we could take of this size produces a confidence interval. So you should think of thousands of people going off and taking their own sample of college students. Each person gets a different interval because they ask different people, slightly different intervals. 95% of those intervals, so 95% of samples, will produce an interval that contains the actual parameter we're looking for. We'll never know what that parameter is, so we don't know which 95%, but we can be very sure that 95% of them will manage to contain that unknown number. This means that when you produce your interval with your data, you have a 95% chance of producing an interval that contains the true value. That is the sense in which you are 95% confident. But the really important thing that people have struggle with is 95% is a percentage of samples. It's not a percentage of students, it's not a percentage of beliefs or anything else. It's a percentage of samples because the random variable p hat takes as its sample space all samples. Let's do another example. Give a 99% confidence interval for the proportion p of Connecticut residents with iPhones, if in a simple random sample of 60 Connecticut residents, 21 had iPhones. Okay, so the answer is the 99% confidence interval for the proportion of all Connecticut residents with an iPhone is, there's my sentence, there's my formula. I'm going to plug in for p hat 21 divided by 60, because the proportion in the sample is 21 over 60. Make sure you get that. This is a new wrinkle. I've given you the number of successes and the total you have to divide to find the proportion. My z star is 2.576 because we had a 99% confidence interval. And my n is 60. So I think we're going through that. 21 over 60 is number of successes divided by total. 2.56 is the z-score of 99%. 21 over 60 again is p hat, and 60 is the number of residents. I will leave you to do the Excel or calculator, but make sure that you do it and get the same answer as me. We end up with 35% plus or minus 15.9%. Notice in our last example, we had a margin of error. We had a sample of about 1,000, and we had a margin of error of 2.5%. Those are pretty typical numbers. This is a much smaller sample, and also the 99% makes for a bigger margin of error. We need a bigger target if we need to be 99% sure of hitting it. So you see a very large margin of error, 15 or 16%. Okay, let's check the assumptions. You check them, and then when you've done so, compare to what I did. Simple random sample. Yes, it says so. Large population. What would we need? We'd need there to be more than 20 times 60, which is 1,200 Connecticut residents. Are there more than 1,200 Connecticut residents? Of course. There are more in the town of Fairfield. And finally, the rule of 15, we'd need both n times p hat and n times 1 minus p hat to be at least 15. 60 times 0.35 is 21. That's good. 60 times 0.65 is 39. That's good. Both are more than 15, so it's fine. And notice here that the n times p hat ends up being the number of yes answers in your sample. N times 1 minus p hat is the number of no answers. So another way to say this is the number of successes and failures in your sample both have to be at least 15. Okay, now you try. Do the whole problem at least until you get stuck. If you get stuck, go back over the previous example and see if you can get yourself unstuck. And then when you're done, compare it to what I've done and see how you did. Give a 90% confidence interval for the proportion P of deer ticks in Fairfield infected with Lyme's disease, supposing that in a sample of 200 deer ticks, 135 are infected. Okay? We report the 90% confidence interval for the proportion of all deer ticks in Fairfield infected with Lyme's disease is p hat plus or minus z star c times the standard error. P hat is 135 over 200. Z star c is 1.645 because of the 90% figure. And inside the square root, we put p hat, we put the quantity 1 minus p hat in parentheses, and we divide by n. So that's 1.645 goes with 90%. P hat is the proportion of deer ticks in Fairfield divided by n, and that works out, again, doing my calculations off camera, to 67.5% plus or minus 5.5%. We had a sample size that was in between the previous two, and we end up with a margin of error that's in between the previous two. Let's check our assumptions. Simple random sample, it doesn't say, so it's not met. Large population, we'd need there to be more than 2 times 200, which is 4,000 deer ticks in Fairfield. Population was deer ticks. You have to be clear on the population to check this. Seems likely to me there are lots of deer ticks out there. So I would assume that's met. If you're not sure, you can always say, we'd need there to be more than 4,000 deer ticks in Fairfield, and I would know you had done it right. Rule of 15, we need both the number of successes, which is 135, and the number of failures, which is 65, to be more than 15. They both are, so that's met. Okay, here's what you should know. After watching this lecture, you should be able, basic fact, to find the confidence interval for a population proportion B given the confidence level, the sample size n, and the sample proportion p hat, or if you know n, the number of successes is enough. You should be able to express the result in a complete sentence including the confidence level, full parameter, point estimate, and margin of error. You should be able to check the three assumptions, and you should understand what the confidence interval means in this instance, and once we've had time to think a little bit, you should be able to interpret the confidence interval as a probabilistic statement. It is saying, it's making a probabilistic statement about samples. It's telling you what is true of a certain percentage of all samples. Next time, we'll talk about means and numerical variables.